Hello, it's Jim from JetsonX.com. On today's show, we are working with USB cameras. This is part of the In Practice series. I have a webcam attached to the Jetson. Let's list the USB devices. Let's sing the song, LS USB. And here it is. In the Jetson camera architecture, USB cameras come in through uvcvideo and then into Video for Linux 2. V4L2 is built into the kernel. Let's take a look at that. We can list all of the modules that are in the kernel. Here's a list of them. Let's filter this a little bit. We will grep for V4L2. And here's all our V4L2-core friends. These are the dynamic libraries that are linked inside the Linux kernel. uvcvideo, which the cameras use to interface with V4L2, is not a built-in module. It is loaded dynamically. Let's take a look at that. lsmod will list all of the modules that are loaded dynamically. And we can see our uvcvideo friend down here. On the Jetson Hex account on GitHub, there is a repository named camera-caps. There is a utility that can help us with V4L2. Let's scoot down here in the README. The name of the tool that we are looking for is V4L2-CTL. It is in the V4L-utils Debian package. Let's install this. Password. Clear this off again. Okay, now we're ready to list the camera devices. You can see that I have 3 cameras connected. This is a Jetson Nano B01. It has 2 Raspberry Pi cameras connected to the camera serial interfaces. Then on our USB port, we have a webcam attached. It's presenting itself as /dev/video2. We can list the pixel formats for the webcam. At index 0, we have YUYV, which is intensity and chrominance. You can think of this as raw. Then we have a compressed version, which is in H.264. And then we have motion JPEG, which is also a compressed format. There's a lot more information available. Okay, we see the driver that it's using. Here are the capabilities. It does video capture, streaming, provides device capabilities, and extended pixel formats. Its current setting is video input 0, 640 by 480, YUYV. Then here's a list of all the capabilities for the webcam. These are parameters that the user can control. For example, take a look at the first one, brightness. It's an integer. It's between 0 and 255. Step of 1, and its default is 128. This is the hex command that you send to the camera to control brightness. There's several different types here. You can have an integer, a Boolean, and a menu, which means that you can select items from a list. We can also ask for all of the pixel formats that the camera supports. Even for a simple camera like this, it's a pretty long list. We can see that the camera supports 640 by 480. You can get support for 30 frames per second to 5 frames per second. The webcam is a USB 2 webcam, so you don't expect to see large raw frame rates. You can see that as we get to larger frame rates, the frames per second drop. 1920 by 1080 is 5 frames per second. And that's why most webcams implement some type of compression. For example, we can see that in mode 1, which is H.264, we get 640 by 480 at 30 frames per second. And even as the frames get larger, we still maintain high frame rates. 1280 by 720 is 30 frames per second, and 1920 by 1080 is also 30 frames per second. This compression is done on board the camera itself, and it's much the same on Motion JPEG. The stream is a little bit larger because of the way it does compression, but you retain high frame rates. For the purposes of this video, I have written a little demonstration. Let's install our demo. Let's install pip. We are using Python 3. And now we install the package that we need. Now let's clone our repository and switch over to that repository's directory. Let's run the demo. And now you can see that this is just basically a GUI veneer over v4l2-ctl.
Gooey, yummy, yummy.
You select a camera. In this case, it's our Raspberry Pi camera. We can see that it has a 10-bit Bayer pixel format. You can get it in several image sizes and different frame durations. Let's switch over to our webcam. And as you saw before, YUIV. This is called YUY2 on Windows. H.264, Motion JPEG, and then the various image sizes. And then the frames per second is the frame duration. Here are the controls that we mentioned. Here's how you set the brightness. There are a couple of convenience features. We have a preview window. I select the size and pixel format that I want to run, frame duration, and hit the preview button. There I am. Hello. Because of the limited bandwidth of USB 2.0, you get a pretty small picture at 30 frames per second. We can use a larger frame format. Let's try that out. Let's go to Motion JPEG. 1280 by 720, 30 frames per second. And we get the same type of performance. This window is a fixed size. It doesn't match the camera resolution. You can have multiple cameras at once. Let's take a look at one of the CSI cameras. 1280 by 720, 60 frames per second. That's not a very exciting view, but you can put a shark in front of it and it becomes a very exciting view. And you can have multiple CSI cameras, of course. Kind of gives you a stereo look at it. I'm going to add a couple more USB cameras. I added a Stereolabs ZED camera and an Intel RealSense. Let's see how they present themselves. Here are two CSI cameras on 0 and 1. The webcam is still on video 2. The ZED is on video 6. Let's open that up. It's a YUIV camera. 2560 by 720. Let's go 30 frames per second. There we go. It's a stereo camera, and basically it presents itself as two RGB images, one on the left and one on the right. The ZED SDK takes these two images and does some very clever image processing with them on the Jetson itself. It overlays them and you get a stereo depth map. You can see that the D415 presents itself a little bit differently. It takes up 3 video devices. Video 3 is Z16, and that's the depth map. Video 4 is one of the infrared images. Let's take a look at that. 640 by 480. Let's take a look at 30 frames per second. You can see the speckles here. And it also presents a RGB color, both in a Bayer image and a YUIV. Let's take a look at that also. And let's grab our webcam. And there you go. All 5 of them. It looks like it's pretty close to real time. There isn't much of a lag or anything. You can kind of tell by the lip sync here. Notice that the colors are all a little bit different, so the webcam versus the RealSense. The ZED is a little bit different than that also. You can see that the webcam has autofocus. The other cameras are fixed. As we talked about earlier, we can control some of the parameters on the camera. For example, the brightness, the contrast, and saturation. Put it back to default here. There's a white balance. I can be warmer, I can be colder. I like being cold. There's a beauty filter. Don't want to be too sharp. Nice and soft. The pan parameter only works when you're using an uncompressed image. And you can put manual focus on it. That's kind of fun. This is even more beautiful. Back to autofocus. Zoom absolute. Oh, that's scary. Right in your face. Back to normal. Then there's one more feature on this little application. Let's open up a new terminal. This is GStreamer code that we can use to launch the camera. Let's copy that. Paste it. And open it up. That gives you kind of a feel for how you actually launch a camera using GStreamer. We're using gst-launch, which is a tool that runs cameras. One thing you'll notice about the Jetsons is that there's a limited amount of USB bandwidth. Even though you have 4 USB connectors, it only goes through one hub. So you have kind of limited bandwidth. Let's open up a RealSense, 1920 by 1080, 30 frames per second. So it handles that fine. Then we'll open up our ZED camera, and you can see that it's still keeping up with it. There's no problem with that. Now when we start adding in the webcam, let's try to go 1920 by 1080 on that. It is not compressed. It gives us about 5 frames per second. So that's pretty good. But we're starting to reach the maximum. So we've kind of saturated our bus at this point. The color on the D415 is pretty good. You can see that the infrared image is a little bit off. And then you can see that the ZED is kind of, well, it's choking a little bit on it. A feature that the Jetson has is USB auto suspend, which means that if a USB port is not being used, it is turned off. So most cameras, they handle that correctly, and they always keep a lane open. However, you may run into a camera that doesn't quite work correctly, and you may need to turn auto suspend off. Now let's go take a look at how we actually integrate camera code into our own applications. Okay, let's take a look at some sample code. On the Jetson Axe account on GitHub, there is a repository named USB-camera. Let's clone that repository. Grab the address. And then we'll switch over to that repository's directory. Let's go take a look at our sample code. There are several different backends that V4L2 can talk to. We're going to look at 2 of them today. One is V4L2 itself, and the other is GStreamer. Let's take a look at V4L2 first. There are several ways that you can interface with the V4L2. One convenient way that a lot of people use is OpenCV. You can use OpenCV as an intermediary to a wide range of backends, including V4L2 itself, GStreamer, FFmpeg, and so on. Let's take a look at our V4L2 backend. We'll just open this up in a text editor. When we were using V4L2, we talked to it using the input-output control, or IOCTL. It's a low-level library which allows you to speak directly to the hardware. It's very Linuxy. OpenCV puts a convenience wrapper around it. In order to run our program, we need to assign our camera ID. Let's use our webcam. Let's check for the address. We can see that it's on /dev/video2, so we need to change this. And we will save it. If we do not select a video format, it will try to select a default one. In our case, let's use YUYV. Let's grab this, copy it, we'll put it right here. And this is about the simplest program you can write for it. We open our camera, we open a window, we read a frame, and then we write the frame to the display. Then we check to see if the user tried to quit out of it, or close the window in this case. So let's try running that. This is a Python 3 script. And there I am, just as we predicted. Let's go for our larger frame. Let's close this up. You may run across this error in your Jetson journeys. Failed to load this module. You can add that module relatively simply. It doesn't appear to make much difference, but it's annoying nonetheless. Let's change this up. Comment that out again. Let's go MJPEG. And let's go 1280 by 720. I think that was at 60 frames per second. Let's save that, and let's give it a whirl. There we are, just as predicted. That's the V4L2 backend. It's pretty straightforward. It's not as flexible as GStreamer. GStreamer is kind of the basis for intelligent video analytics, is what NVIDIA calls it. Let's take a look at the GStreamer sample. Okay, let's see. Pipeline. Assign camera address to device here. Okay, 2. This is video 2. We're going to go 640 by 480, frame rates 30/1. In order to run the frames in OpenCV, we need to have BGR as our output. And we are going to use it in our application. This is very similar to our last application. We open the camera here, open a window, we read the camera, and then we show the frame in the window. And then we check to see if the user wants to quit. So let's take that for a spin. Okay, let's run our program. There we are. Just like magic. GStreamer is a powerful, extendable type of system, which in practice means it can be a little bit difficult to deal with. It takes a lot of kind of finagling to get the best performance out of it. In order to use GStreamer with OpenCV, you always need to have BGR as your pixel format going into your app sync. App sync here is basically the gateway into your application. Let's go for H.264. We use the H.264 pipeline. Let's close this up. Oops, almost forgot. Need to change the video address. Change that to 2. And let's save it. Okay. Python 3. USB dash camera dash GST. There we are. This is H.264. You can see some of the compression artifacts. That's kind of interesting. If I move around, this is pretty low frame rate because this is a USB 2.0 camera. And eventually it will catch up. When you have a USB 3 camera, then it's a lot faster, of course. More bits, better quality. MJPEG is better in this particular application if you have the bandwidth. Look like I'm part of The Walking Dead with this baby. Let's close this up and go to our last application. For our last sample, we are going to use a cascade classifier to detect faces. We're going to use V4L2 as our backend. Assign the camera address here. It is number 2. Let's just run it on the 640 by 480 to start off with. This will open the camera. We'll open our window. Then we'll do our face detection and eye detection. Let's make sure we save it. Let's take it for a spin. Face detect. There we are. So it looks like it can detect faces. Eye detect seems a little challenged. That's interesting. Looks like it needs to be pretty straight on before you see a face out of it. The face seems to be pretty good. I don't trust the eyes here. Maybe it's a lighting thing. But it's a pretty good little sample application. Now, when you're using OpenCV in this manner, there's a couple of things you need to watch out for. If you're having issues with GStreamer or V4L2 or GTK, you can look at the build information. That will give you a clue as to what's going on. Let's fire up Python. And we will import OpenCV. It's called CV2. And let's print the build information. Here's a couple of the things that we are looking for. For the GUI, in this example, we are using GTK. OpenCV can also use Qt for its GUI. And then down here in your video I/O, you want to make sure that you have GStreamer support enabled. Yes. And you want to make sure that you have V4L enabled also. This is the default OpenCV build for the Jetson right now, OpenCV 4.1.1. If you're going to use these features and you compile your own OpenCV, make sure you include these options. So that's, in practice, USB cameras. If you liked the video, give it a thumbs up. And if you have not already, please subscribe. Thanks for watching. Oh, stay safe.